Welcome to a interesting discussion on an application of polar coordinates that you may or may not have experienced before. Most of you, I imagine, haven't. This is where you really get your money's worth for this class. We are going to look at polar forms of complex numbers. So we're going to start off with a very innocent sounding question. That's what we're going to do in this video, and then we are going to work towards a more difficult answer, and then still more complicated arithmetic. So let's get to it. Let's ask one of the easiest questions that I've ever asked. What is the square root of I? What is the square root of I? Now, I mean, that on the surface, that sounds rather innocent, right? The square root of I is the square root of -1, so it's the fourth root of -1, right? Well, that's true, but that's missing a little bit of information. Because you see, I know that every polynomial has complex roots if it has complex coefficients. That was actually the whole point of algebra. If you've not seen that, then you might want to reconsider the algebra courses you've taken up to this point. 1710 focuses rather heavy on it, but every polynomial with complex coefficients has complex roots. So in particular, this one right here, x to the fourth plus 1, every single root for this guy is complex. Well, you can solve for all the roots here, right? X to the fourth is equal to -1 if and only if x squared is plus or minus I, if and only if x is plus or minus square root of I, or plus or minus square root of -I, right? Those are all the fourth roots of -1. So, well, great. But, again, these have to be complex numbers. These have to be equal to some a plus bi complex number. So, to re-ask the question, the square root of I equals an a plus bi complex number. What is that complex number? Or in other words, find a and b so that root I equals a plus bi. And it's going to be rather difficult to answer. In fact, so difficult that I've just went ahead and told you what the answer was. And even then, going from start to finish is not necessarily that easy. You see, if square root of I is equal to root 2 over 2 plus root 2 over 2i, that means they both have to square out to be the same thing, right? If they're the same before you square them, they have to be the same after. And so, indeed, we actually get that happening, right? You square root I, you get I. You square root 2 over 2 plus root 2 over 2i. You get the first term squared, the last term squared, and 2 times the product. So that's going to be a half minus that half, and in the middle is 4 over 4i. So yeah, that's got it. That is the square root of I. Now I know what you're thinking. Why is negative root 2 over 2 minus root 2 over 2i not the square root of I? Because that also squares out to be I as well. Well, we'll get to that. Don't worry. We'll get to that. Good question, though. You're very observant. But this seemed like it was pulled out of the blue. How in the world would we possibly be able to decide how to get here from just starting at I? And to answer that question, we are going to have to do some constructing. You see, we're moving away from the Cartesian plane entirely this time. You know, the Cartesian plane was two axes. One was for one set of real numbers, x values usually, and the other axis is for other sets of real numbers, y values. And so all the points on the Cartesian plane were x comma y. They were ordered pairs. Well, now the complex plane works a lot the same, except instead of for it being two pairs of, or a pair of two real numbers, it's going to be one single complex number. You see, a plus bi, the standard form for a complex number, has a real part and it has an imaginary part. So you have 1 minus 2i. The real part is 1 and the imaginary part is negative 2i. So you would plot that one single number across two axes, one for the real and one for the imaginary. And this plane covers all possible complex numbers. So every single number that is complex can be put on this plane. Now we can't have pairs of complex numbers in the same way we had pairs of real numbers, right? A pair of complex numbers would take 4 dimensions, and I'm not doing that. So we'll just worry about one complex number at a time if that's okay with you. And as we'll see in the next few videos, that is enough. That's asking for enough. Now, that is how we would plot 1 minus 2i. That is how we would plot a plus bi. So the xy coordinate of a Cartesian plane is totally analogous to an a comma b coordinate, right, on the complex plane, right? That you could kind of justify this to be a comma b, right? 1 minus 2, except we have a label of I on the y-axis. And you're not entirely off base. In fact, that is going to be exactly the reason why we're about to do what we're about to do. How far away from 0, 0i, or 0 plus 0i, how far away from the origin is this point? Well, I would inscribe a right triangle. The a value, the x value, the base is 1, the height is 2, and so r is the square root of the sum of the squares, right? The Pythagorean theorem still applies. And now, also, just like what we've been doing before, I can find this angle of rotation that would get a line segment of length r down to this exact point, just like we did with polar forms already. So here we go, right? If you have a plus bi on the complex plane, the distance from the origin, right, the r value, the radius almost, right? Actually there is a thing for circles in a complex plane, but we'll get to that probably never. Anyway, the r value is as it was in the rectangular world, right? A squared plus b squared equals r squared. So you take the square root of that, you have your absolute value. You have your distance from the origin to your point. You have your line segment. And then the angle of rotation, as before, satisfies tangent theta equal b over a. And you kind of have to, again, recognize that that only will give you first quadrant or fourth quadrant if you did the arctangent, so you would have to, adjust accordingly. But based on that, I now have a is equal to r cosine theta and b is equal to r sine theta, just like before, right? X was equal to r cosine theta, y was r sine theta, so now a plus bi becomes r cosine theta, r sine theta, I. And I have it written this way because people would look at having an I over here and think, well, is I inside the argument of sine or is it outside? So I just write I out over here so there's no doubt. And of course, when we factor out the r, this is your standard polar form of a complex number. R is your distance from the origin, theta, your angle of rotation. And that is exactly what we've been doing with polar forms already, but now we're going to do even more with that. So I just have one quick question for you, making sure you can convert now complex numbers into polar forms. And we'll go from there. Have a good one.